Good morning, and welcome to the 2015 Mars Society Convention. If you will, if you're on social media, you can tweet or Facebook hashtag MarsCon2015. I have been a huge fan of Humans to Mars since I read the National Geographic article Humans to Mars in 1988. And shortly after that, I discovered Dr. Robert Zubrin's work, and I've been obsessed with going to Mars since that moment. It is my great pleasure to introduce one of my biggest heroes, Dr. Robert Zubrin, President and founder of the Mars Society.
Thank you. America has a number of symbols it's famous for. Got the flag, there's the American eagle, but my favorite, and I think probably the most popular of Americans' symbols, popular across the political spectrum from left to right, fairly popular around the world, Statue of Liberty. You should know that while we today, most people anyway, sometimes view the Statue of Liberty in the light of Emma Lazarus's poem, that is, she's welcoming immigrants to America, and that's fine. That is not how it was originally conceived. The original name of the Statue of Liberty is Liberty holding her light, shining her light on the world. And she's facing east to Europe to shine her light to Europe, to the world. Okay, that's what that statue is about. Okay, that we are shedding light of a new way of doing things to the rest of the world, showing the way. Now, space program began, substantially as an effort to show the light. Okay, literally to show the light of freedom, to astound the world with what free people can do. That was the purpose of the Apollo program. That is, the way forward for humanity was being challenged by advocates of despotism, and we wanted to show the world, astound the world with what free people can do. And in fact, we did. Okay, I myself was in Leningrad when we landed on the moon. Okay, that's where I was when we landed on the moon. Everybody remembers where they were when they landed on the moon? I'll tell you exactly where I was. The leadership there may have been having kittens, but I got to tell you, the Russians loved it. At least the ones I knew. Come up to me, punch me on the shoulder, molodets. They got it. And people elsewhere got it. And I would say that accomplishment did much more to achieve America's goals in the Cold War than its parallel deployments in Vietnam at that time. Which were far more costly and accomplished very little. Now, it's people, wonder at how much we accomplished in the 8 years between Kennedy's speech and the moon landing, and it's sometimes said, well, they did it because they had much more money. And they point to the fact that the NASA budget during the Apollo period was a much higher percentage of the federal budget than it is today. And that is true. It was a much higher percentage of the federal budget. But that is because the federal budget was much smaller, was 1/4 as great in current inflation-adjusted dollars. Okay, NASA's actual budget in inflation-adjusted dollars during the Apollo period, which I take from 1961, Kennedy's speech, through 1973, the Apollo Skylab missions, okay? If you take all the money that was spent in NASA over that period of time, you translate it in today's dollars, okay, and you add it up and divide it by 13 years, comes out to $20 billion a year. NASA's budget this year is around $17 billion. That is, in rough terms, the NASA budget of the Apollo period was about the same as it is now, and as it has been since about 1990. Okay, there was a post-Apollo period when it went substantially lower, but it started going back in the 80s, and by about 1990 it got back to approximate Apollo levels, and it's been there ever since. But the level of accomplishment has not been comparable, not remotely comparable. In 8 years, okay, we did Mercury, Gemini, Apollo, Skylab. We did Ranger, Mariner probes to Venus and Mars, Pioneer probes to Jupiter. We developed hydrogen-oxygen rocket engines, multi-stage heavy-lift launch vehicles, in-space life support, space rendezvous techniques, deep space navigation techniques, deep space communication techniques, the ability to soft land on the moon, radioisotope thermoelectric generators, spacesuits, life support systems. So not only did we do far more missions, both manned and robotic, we developed far more technology. Okay? And we did it on approximately the same budget that NASA is functioning on today. Okay? Now, what, therefore, was the difference? Okay? The difference is that NASA in that period of time was mission-driven. Okay? You can either be mission-driven or you can be constituency-driven. Okay? There's, if you compare, and this is particularly, and I'm really addressing here most importantly the case of the human spaceflight program. Okay? Because the robotic spaceflight program has remained significantly mission-driven, which is why over the next several days you're going to get a string of people walking in here talking to you about the recent accomplishments of the robotic space exploration program, both on Mars and elsewhere, but you will have no one coming in here talking to you about the recent accomplishments of the human spaceflight program. Okay? It's not because I didn't invite them. Okay? Okay. Now, what's the difference? I mean, we recently had a NASA administrator, Sean O'Keefe, who said NASA should not be destination-driven. He actually said that out loud, with emphasis, which meant NASA should not have any particular goals, that it should just kind of function and do stuff, and we'll let you know when we're ready to do something. And the contrast to that, okay, he said it should be technology-driven, that we'll work on technologies, and someday we'll develop the technologies that will allow us to go anywhere, anytime, okay? But that's not true. See, we didn't get to the moon because one day around 1963, some guys ran into each other in the cafeteria at the Marshall Space Flight Center, and one said to another, with your Saturn V and my capsule and his lunar lander, if we put these things together, we could go to the moon. No, that's not how it happened. Okay, the way it happened was Kennedy said, we're going to go to the moon, and we're going to do it by the end of this decade and figure out how to do it, get it done. And they went and they figured out, they designed a plan. The plan determined the technologies that they needed to develop, okay, and determined the spacecraft that they needed to develop. And they then went and developed those things, and they all had to fit together, and they were able to go to the moon. Now, as a side product of that, they were able to take some of that hardware, and they also do Skylab as an ancillary activity. Okay, but in the beginning was the Word. The technology-driven program, as so-called, is really constituency-driven. Once again, to contrast the two modes, consider two couples, each trying to build their own dream house. Okay, one hires an architect, say, okay, we want a house like this, and he sketches it out, and they finally say that's the house we want. Then they hire an engineer, he designs it, and then they bring in a construction crew, they build it. The other goes around cruising garage sales every weekend and buying house parts that they find appealing. Some aluminum siding, a fountain with a statue of Napoleon in the middle, spiral staircase. They pile it all up in the backyard. And then when their in-laws come and visit and pa-in-law says, why do you have all that junk in your backyard? They say, well, that's to build our dream house. And he looks at this pile of miscellaneous things and he says, I'd like to see the plans of this house. So they go and they hire an architect and they say, look, you need to design us a house and it has to include all of these parts. So he has to design this fantastical ramshackle house that somehow includes all these miscellaneous items. And of course, the thing's unbuildable, but it serves the function of providing a rationale for the random purchases that they've already done. Okay. That's the technology-driven approach, so-called, which is actually, once again, a constituency-driven approach. Okay. In the mission-driven approach, you spend money in order to do things. In the constituency-driven approach, you do things in order to spend money. Okay. Those are two different propositions. Okay. And that is the problem. Now, the fact that the mission-driven approach can work is proven, is that it can still work, that NASA can still do it, that NASA is not senile, that they have not, lost their minds, is the fact of the success of the parts of NASA that remain mission-driven, which includes the robotic exploration program. Okay, but see, we didn't do Spirit and Opportunity in order to be able to use airbags. Okay, we used airbags in order to be able to do Spirit and Opportunity. In other words, they thought of how they were going to do a rover mission of a certain class. They thought of what would be appropriate technology to land those rovers, and then that's the technology they developed. Okay, that's how it's got to go. Okay, now the human program needs a goal. Okay, not a rationale. Okay, a goal. There's a difference between a goal or a reason and a rationale, which is an excuse. Okay, so it needs to be doing something not to do something. It needs to be doing something in order to accomplish something. Okay. So what is it that humans can accomplish in space that is unique, something that is truly worthy of the cost and risks of human spaceflight? Okay. That, in my view, is humans to Mars. Okay. Mars. Okay. Not just humans in space to be in space. Okay. Not humans in space in order to visit a asteroid fragment. You could do that at the Rose Planetarium. And if they want to do that in space, we could take one out of the Rose Planetarium and launch into orbit and then visit in space. No, but that wouldn't make any sense, right? Mars is where the science is. Okay, Mars was once a warm and wet planet. Got lots of evidence of that. It had liquid water on it for a period of time longer than it took life to appear on Earth after there was liquid water here. So if the conjecture is correct that life is a natural development out of chemistry, wherever you have warm and wet conditions on a planet with the various elements and sunlight and so forth for a sufficient period of time, then life should have appeared there. And there should be some evidence it left behind, even if it subsequently went extinct when conditions on the surface of the planet deteriorated. Okay? So we could look for fossils on Mars. or the life may still exist on Mars, because there's substantial evidence that there's liquid water underground on Mars, and there is life in underground liquid water on Earth. And in fact, the surface of the Earth today is uninhabitable for the Earth's original inhabitants, which were organisms which could not tolerate oxygen. Okay? Photosynthetic organisms made the surface of the Earth uninhabitable to the natives, okay, by polluting the atmosphere with horrible oxygen, okay, toxic oxygen. So they had to go underground, and they've been there ever since. And they outnumber us, by the way. They're waiting their time. But there they are. And if we go to Mars and set up drilling rigs and drill down and reach the groundwater and bring up a sample, we might find Martian life. And if we could find Martian life, we could look at it, analyze it. We could find out if life as it exists on Mars is the same as Earth life, because all Earth life at the biochemical level is the same. It all uses the same amino acids, the same RNA, DNA system of replicating and transmitting information, okay, which is really quite esoteric if you think about it. Is that what life is, or is that just one example drawn from a much vaster tapestry of possibilities? This is worth finding out. Okay? And also, since we now know from the Kepler Space Telescope that planets are everywhere, that planets around stars are not the exception, they are probably the rule, and since every star has a habitable zone, near or far, depending upon the brightness of the star, where you have the right kind of temperatures for liquid water, if life is everywhere, I mean, if life can evolve from chemistry as a lawful process, it means life is everywhere. And since the whole history of life on Earth is one of development from simpler forms to more complex forms, manifesting greater capacities for activity and intelligence and ever more rapid evolution, if life's everywhere, it means intelligence is abundant as well. It means we're not alone in the universe. This is something that thinking men and women have wondered about for thousands of years. This is worth risking life and treasure for. Okay. So, we need to go. And we need to stop dodging the challenge. You know, in 2001, Mars Odyssey did the transit to Mars, and by the way, in 6 months, launched in April, arrived in October. That's how long it takes to fly from Earth to Mars using current propulsion. Okay? And it measured the radiation in interplanetary space. And it measured it to be basically twice as much as it is at the ISS, which is something I could have told you in advance. Okay? Because there's the cosmic radiation, because the Earth's magnetic field does not effectively block out cosmic radiation. The ISS is shielded from half the cosmic radiation it might get because the Earth blocks out half the sky. You go into space, it's going to be twice as much. And that's what Odyssey measured. And the instrument called MARIE on Odyssey. And NASA, they published the findings, and they said this shows that radiation is not a showstopper on the way to Mars. It's only twice what we're experiencing right now on the ISS. Okay? In 2012, Curiosity went to Mars, and they had an instrument on it, and either 13 or 14, they published some results. And guess what? It also measured the radiation field in interplanetary space was twice what it is at the ISS. And many of the investigators on that were the same. And they said, oh my God, the radiation field in interplanetary space is twice what it is at the ISS. We can't go to Mars. Okay, this is like, there's this Woody Allen movie. I forget which one of the older ones, is with Diane Keaton. And they go to a shrink, and separately, because they're having problems with the marriage. And they both agree that the marriage is in trouble because their sex life is terrible. And Woody Allen says, she only wants to do it 3 times a week. Can you imagine that? And she says to him, he wants to do it 3 times a week. Can you imagine that? The same data, different spin. Okay, but basically, interpreting the radiation field as being a showstopper on the way to Mars is like a 10-year-old kid looking out the window and seeing some snow and saying, looks like it's going to snow, can't go to school. It's a snow day. It's much too risky. Okay. You got to want to do it. You got to embrace the challenge to do it. Now, Jesus. Okay, does this work? Okay, there's one thing. So we don't need stuff like this before we go to Mars. Giant nuclear-powered interplanetary spaceships that allegedly can get us to Mars in 39 days if you accept ridiculous mass estimates for the nuclear power system. And this is why, by the way, I repeatedly challenged Chang Diaz to debate his claim we can't go to Mars until we can go there fast, and secondly, that his system can get us there fast, and therefore we can't do our program until we do his program. But no, it's not, first of all, that system can't get you there fast, and you can't get that system, okay, because it can't exist. And we can do Mars. I mean, the radiation is not a showstopper. And in fact, the proof that the radiation is not a showstopper is NASA's currently accepting the radiation risk, because on the ISS program, if you can, okay, ISS, they're half the radiation dose rate of interplanetary space. So let's say ISS crew is about the same size as the Mars crew, which it is. Over the next 10 years of occupying the ISS, we'll have 10 ISS crew years worth of radiation. If over 10 years we launched 5 crews to Mars, because you can only go to Mars every other year, and each crew spends a year in space, because 6 months out, 6 months back, year and a half on the surface, but you can have lots of shielding there. Okay, so over that period of time, over 10 years, they'll be spending 5 years in space at twice the radiation level of ISS. You'll also get 10 crew years. In other words, they are going to have exactly the same amount of exposure in manned REMS over the next 10 years in the ISS as they would sending 5 human missions to Mars over its decade period, okay? But since that is where they have a constituency to spend money, that it's not a showstopper there. The radiation is not a showstopper, okay, at all. Okay, it is in fact a modest portion of total mission risk. The radiation dose that you would get on the way to Mars and back is represent about a 1% risk of getting cancer at some point later in your life, assuming no advance in medical technique. That is a modest portion of overall mission risk. Okay, the idea that you would spend tens of billions of dollars on a technology like this, and also tens of years, which involves hundreds of billions of dollars of loss of funds through loss of time, okay, because NASA is like a taxi and the meter is running whether it's moving or not. So you really want it to drive, okay? Okay, in order to, say, reduce from 1% to 0.5% the risk of cancer to 5 people, that you would spend, say, $50 billion to reduce the risk of cancer by 0.5% to 5 people, when with $50 billion spent on medical care, you could save the lives of millions of people, okay, or tens of thousands, I don't know the exact number, depends, but it's a large number. Then you're actually committing what's known as statistical murder. That is to say, spending money on nominally life-saving activities in preference to spending it much more effectively on life-saving activities. Okay. Now, so we don't need this. Okay. True, we'd like to practice before we go to Mars, and people say we got to have a moon base to practice. No, we don't need to have a moon base to practice before we go to Mars. We can practice in the Arctic or the Antarctic at 1/1000th the cost. We do need, I believe, a heavy lift launch vehicle. Okay, this was one we designed way back in 1990 when I was at Martin. This was a shuttle-derived heavy lift launch vehicle. The engines are offset thus, so you could use the shuttle launch pads, which have the flame trenches there. The vehicle like this today, and the whatchamacallit, what SLS is kind of like this. You'd put the engines here. It'd be a little better. This was because it was parallel with the shuttle. But if you built a vehicle like this with a hydrogen, oxygen core, solid strap-ons, hydrogen, oxygen upper stage, you could build a vehicle that could throw about 47 tons directly to Mars on direct trans-Mars injection, or 59 to the moon if that's what you wanted to do. Okay, so the way you do a Mars mission in this approach is known as Mars Direct. And if you need the details, I got a book on the subject. They got it on the table. It's called The Case for Mars. Okay, you launch in your first operational year 1. One booster sends an Earth return vehicle on a minimum energy trajectory to Mars, unmanned. It lands on Mars. After it lands on Mars, this is what it is. It's a small Mars ascent vehicle with a modest cabin that can accommodate a crew of 4 on a 6-month transit back to Earth in the last part of the mission. A couple of methane, oxygen propulsion stages that are unfueled, except it's got about 6 tons of liquid hydrogen in some of the lower stage tanks. And not shown in the diagram, a small nuclear reactor, 100 kilowatts, on a light truck that can deploy at a couple of 100 meters away from the landing site. You get it there, you turn it on, you got power, you run a pump, you suck in the Martian air, which is carbon dioxide gas. You can react carbon dioxide with hydrogen in the presence of a catalyst. It will produce methane and water with great specificity. And this is exothermic, doesn't need any energy. The methane's your fuel, you store that in your tank, you electrolyze the water, produce hydrogen and oxygen. The oxygen is your oxidizer, the hydrogen you recycle to make more methane, and then to get additional oxygen, you run a splitter that takes CO2, split it into carbon monoxide and oxygen, keep the oxygen, dump the carbon monoxide. It's legal on Mars, no EPA. EPA is banned on Mars. Okay, they have been banned because they're going around spilling toxic waste into rivers on Earth, and we don't want them on Mars. Now, and by the way, the Mars 2020 rover is going to have an experiment demonstrating this process. This other one is actually simpler, and it's been demonstrated in the lab by that person. So now you have a fully fueled Earth return vehicle sitting waiting for you on Mars. Then at the next launch window, you launch 2 more boosters off the Cape. One shoots out another Earth return vehicle. The other shoots out a habitat with a crew of 4 astronauts in it. Okay, simple tuna can hab, bigger though than the chicken of the sea design, is 8 meters in diameter, tall enough for 2 decks. Upper deck is habitation, lower deck is cargo hold and workshop. Here's one design, the upper deck of the hab, 4 little staterooms, science, exercise, wardroom, solar flare, storm shelter in the center, shielded with provisions. You have enough provisions on board a mission of this character to shield a limited area of it against solar flares, because water and things like water, such as food and metabolic waste, are ideal shielding against solar flares. You cannot shield against cosmic rays, but as I mentioned, the cosmic ray dose is not that big, and in fact, there is about 10 astronauts and cosmonauts that have already received cosmic ray doses due to missions on ISS or Mir or the Salyut space stations that are comparable to that they're getting to Mars and back, and we have observed no radiological casualties whatsoever. Okay? We have observed, of course, health deterioration from 0 gravity, but there is a counter for that, which is rotating spacecraft. And so you can have the spacecraft, you tether off an upper stage. The upper stage that threw it to Mars, which it's at the end of that tether. You can't see it in this light, but it is there. This tether is 1.5 kilometers long, about a mile. You spin this at 1 RPM, you create Mars gravity in the hab, and that keeps the astronauts in good physical shape. You could go to Mars in zero gravity. You can certainly survive 6 months in zero gravity. The ISS crews do it all the time, but they come down deconditioned. And you don't want to do that on a human Mars mission because the purpose of the mission is exploration, which involves hiking around in a spacesuit on Mars, and the degree to which someone will be able to do that, the level of the activity, will be in proportion to their physical condition, and therefore it makes no sense to send them there in a deconditioned state. And the idea that people raise objections to spinning the spacecraft to avoid zero gravity is like the doctors in 1942 who objected to oxygen masks on B-17s. They said, well, no, that's complicated engineering. You want to find a pill that will solve hypoxia. I'm not making this up. Read Scientists Against Time by J. Baxter Finney. This is the story of the wartime R&D effort. But because clearly solving the problem of controlling a rotating two-body spacecraft is much simpler than altering human physiology. Okay? So there you have it. So you can get them to Mars in good shape. Then when it's a 6-month transit to Mars. And by the way, if you had an advanced propulsion system, and I'm not talking about even a science fiction propulsion system like the ultra-fast Vasimir, but a more realistic system like nuclear thermal rocket engines, you still want to go to Mars in 6 months, not in 3. Why? Because the 6-month transit to Mars is the free return orbit. That is, if the orbit that gets you to Mars in 6 months, if you decide not to stop at Mars, you could go past Mars, you go out to around 2 astronomical units from the sun, and you loop back and you reach Earth's orbit exactly 2 years after you left, okay, so that the Earth will be there. Okay, if you were going faster, you would go out further, and then when you'd come back, it would be more than 2 years. Now, there is another specific trajectory, a little faster, that you'd come back in 3 years, then 4 and 5 and so forth. But if you try to get to Mars in 39 days, you're on a very fast trajectory that if you don't stop, you're not stopping. Okay, I mean, you're going to infinity and beyond. And so in fact, the safest way to go to Mars is to go on the 6-month trajectory, which also, by the way, is a pretty good choice in terms of the trade of delta V propulsion requirements against cargo. That is, if you try to go faster, it takes a lot more propulsion, and you reduce the mass you can send, which reduces the redundancy of your life support systems and things of this sort. So it turns out that for human missions, 6 months is the right way to go. Okay, for cargos, the 8.5-month minimum energy trajectory is the best. But so they go out, they get there in 6 months, cut the cable with a pyrotechnic device. They go and land at site number 1 where the fully fueled Earth return vehicle is waiting for them. If there's anything wrong, they can always bring this one down to land near them, or if they land imprecisely or on the wrong side of the planet, we can bring this one to land near them. Otherwise, we land it at a new place where it starts making propellant to support the next mission, which flies out there 2 years later, along with another Earth return vehicle, which is their backup, but which otherwise opens up site number 3. So this is an actual photograph of the base. Okay, there it is, although a little artistic license here in putting things probably a little closer together than you'd want, but that's the Earth return vehicle, that's the HAB, that's the reactor, this is their ground rover, this is an experiment, inflatable greenhouse. And they can explore Mars for 1.5 years and then get in the Earth return vehicle and fly back to Mars, leaving the HAB behind on Mars. So you can either keep adding HABs to a base and build it up, or you can land in a dispersed pattern to explore wider regions before you decide on where you're going to do a concentrated landing and land at a base. Now, and you can use the same hardware to build lunar bases too. I won't go into that in time, but the point here is this. This is the point. There's some technologies that have to be developed to show you what, to do what I just showed you. There's no doubt. But I have to tell you, the technical challenges of doing what I just showed you are much, much less than the technical challenges that this country faced in 1961 in sending people to the moon. Okay? That is, relative to today's technology, this is a much smaller challenge. We are much closer today to being able to send humans to Mars than they were to being able to send men to the moon in 1961, and they were there 8 years later. Okay? Now, so they could do it. They could do it with a United States that had 1/4 the GNP of the current United States. Okay? People say, oh, it was a much bigger percent of the GNP, much bigger percent of the national budget. That's because they were poorer. Okay? And yet they did it. And for us to say that we can't do it is for us to say we've become much less than the kind of people that we used to be. And that is what this country cannot afford. And that is what we need to tell, what you need to tell these presidential candidates that are running around right now, that for once, for a few months, every 4 years, the political class makes themselves accessible to you at shopping malls and bingo games and, church socials and whatever, okay? They're out there eating donuts at Dunkin' Donuts, and you can go up to them, okay, because they're there pretending to be one of us, right? And and you can say to them, what are you going to do to give this country a space program that's worthy of a nation of pioneers? Have you accepted American decline? Okay, what are you going to do to give us, American people, we want a space program that is actually going somewhere. What are you going to do? You want to know something? They'll talk to you, because they'd actually much rather talk about this than about the gotcha issues everybody else is hitting them on. Okay, and maybe you'll reach them. We got to do it. Okay, we need to reaffirm who we are. Okay, we need to reaffirm ourselves as a can-do nation. We need to shine our light forth again. Okay, we need to, once again, we're being challenged. America's being challenged by Putin, by the Islamists, by China. We need to, once again, astound the world with what free men can do. Okay? And that means we need to accept the challenge of Mars. Thank you. I've got a few minutes for questions, so I'll take some questions. Sir. 90.
Okay, so I'm supposed to, because I read your report years ago, and don't you think we should just, with all due respect to the good people at NASA, why don't we just fund this privately, we get this off the ground really figuratively? I mean, I don't know, you've done this before. Let's say you had, I know you came up with a proposal,
Okay.
you actually had a budget, and you didn't come up with a number. And I don't know what that would be in today's dollars, but let's say 10 years, it's $40 billion. I'm just using the figure. Okay. I think that in this day and age, with all the people and the brains, with you, Spirit, and people like Elon Musk and everyone else, that we could privately fund this and just bypass all the bureaucracy, get it all figured out. And all of us, including me, I would thought.
Okay, well, let me answer your question, because it's an excellent question. The question is, why don't we just fund this privately? Okay, now, and actually, yeah, you came up with a number that was in the ballpark of our estimate for a Mars Direct program involving developing all the technology and flying 5 missions to Mars and also several to the moon. It was about $40 billion. Okay, and I think NASA, if it was focused on accomplishing it, okay, if it was focused on accomplishing things by spending money rather than doing things to spend money, okay, could do it in that range. I think if it was done in the private sector entirely, it probably could be done for more like 10, because $10 billion is actually a lot of money in the real world. Okay, but okay. However, It's a lot of money, okay? Now, Elon Musk is doing great things. SpaceX is doing absolutely great things. And they are showing that they can develop hardware in 1/3 the cost, excuse me, 1/10 the cost, 1/3 the time that has been accepted as generally required in the manned spaceflight world. They developed a medium lift launch vehicle for $300 million, and the Dragon, similar money. And this is great. They're spending, Elon is spending money like it's his, because some of it is. And that's important, okay? That is important. And certainly the systems that they create will greatly enhance the possibilities of humans to Mars, because by lowering the cost, they lower the threshold. I mean, see, look, the opposition to humans to Mars in the political system, it's not like opposition to the Iraq War or something, where some people are against it because they are, in fact, against it, okay? The opposition to humans to Mars does not come from people who are opposed to humans to Mars. It's people who are opposed to spending money on humans to Mars as opposed to other things, okay? It's a different story, okay? And therefore, to the extent the cost can be lowered by creating flight systems, I mean, look, he's developing a heavy lift launch vehicle mostly on his own money. The Falcon Heavy, Augustine Commission said it would take 12 years and $36 billion, which is to say 4 times the cost of the superconducting super collider, to develop a heavy lift launch vehicle. Okay, by having that vehicle out there, that changes the arithmetic. But that said, spending $10 billion of his own money, Elon Musk doesn't have $10 billion, okay? $10 billion is a lot of money when it's yours, and especially, I checked, I don't have it. Okay. So for now, the best I think we can do is, first of all, to give Elon our support and make sure he's not knifed in the back by people who want to stop him, because there are some who do. But also, the goal has to be there. If we can get it accepted as a national goal that we should send humans to Mars, then the fact that Elon's got this hardware that could cut the cost of it by a factor of 4, that greatly enhances the case. So the two things both work together. Sir?
Yeah, it's 2 questions, not necessarily for you, but also for the general audience. So perchlorate, 1 atom of chlorine, 4 atoms of oxygen. It's about 2/3 oxygen by weight. There's a reason to believe that on Mars there's a large amount of perchlorate that could be mined. What's missing is a low temperature catalyst for releasing solid oxygen into the Does anybody know, and in fact I'll be here all the time, so if anybody knows about a low temperature catalyst for the synthesis of oxygen from perchlorate we could use?
Well, oxygen was released from Martian soil by exposure to water on Viking. But I don't know if it would have been released. It doesn't look to me like that was in useful amounts. The easiest way to make oxygen on Mars, the most reliable way, is from the atmosphere, because its composition is predictable and it's everywhere. No, excuse me. I'm going to get one more question and we're going to wind up. Miss.
I have a question about the Martian movie that's going to be coming out soon based on the book.
Yeah.
Are you hopeful that that's going to really spark the public interest in this kind of program, and that possibly maybe after the catalyst, the bureaucratic and political naysayers to this, or do you have other concerns?
The answer is yes, I am hopeful. And in fact, that's one reason why Andy Weir is going to be speaking to this conference on Saturday night. I mean, there's one thing that I don't like about The Martian, which is what the movie is about getting back from Mars. And if that's your primary objective, is getting away from Mars, there's easier ways to do it. But nevertheless, I like The Martian overall, the same reason I like Apollo 13, is what it shows. I mean, look, it's the same message that Homer had in the Odyssey, is the man who uses his wits can overcome the unknown, You stick with Athena, you can defeat Poseidon. the mind over the threats of nature and the unknown. That is, we can do it. It's about human grit. It's about the fact that we can defeat the dragons that are on the map, that we have the stuff. Okay, so let's do it. And I mean, look, why was Apollo 13 so popular? Because it reminded us of the time when we showed we had that character. And of course, this is fiction. This is about the future. But it's saying to us, come on, fellas, this is you. Let's do this. And I think that Americans are going to respond very positively to that. Thank you.